All right, let's get started. So welcome everybody to the second exoplanet session of the conference. This is the first parallel session, session 3.1. This afternoon, we will have 4 talks. And the first up will be Michael Gully-Santiago from the University of Texas at Austin, who will be talking about condensate cloud modulation on ultra-cool dwarfs. So whenever you're ready, take it away, Michael.
Okay, great. Thanks, Ian. So yeah, let's go ahead and screen share and play. Okay, great. So thanks for having me today. And today I'll be talking about clouds seen in both TESS and the IGRINS spectrograph. Okay, so key idea here is we're targeting lumen 16 AB. So this is a binary brown dwarf system. It's actually, I believe, something like the 3rd closest system to the sun at a mere 2 parsecs away. And this has existing Doppler imaging from CRIRES from 2014, seen here, where you see modulation as in this case, lumen 16b rotates on its axis, and you can see surface structures evident in the line profiles. This system is amazing because it's so close that it's by far the brightest system we have. And so there's a lot that we can do with this system that we can't do anywhere else. It was observed in TESS in sector 10 and reported just recently. But relevant for this talk is that it was revisited in sector 36 and 37 just a few months ago. And so that's what we'll be talking about today. And like I said, it's amenable it's basically the only system that's amenable to such high resolution, high precision spectroscopic time series. Okay, so here's sort of the orbital geometry. It's much less, the separation is much less than 1 TESS pixel at a mere 1.3 arc seconds. And at the moment, it's actually about as separated as it gets, or almost as separated as it gets. And so it's actually resolvable with a scene limited slit spectrograph. So here's an example on the left with IGRINS slit viewing camera, and you can see the A and B components if you squint, and the slit align perpendicular to that axis. And then on the right is the HST imaging, where you see this dance as lumen 16 both moves in its orbit and from proper motion. And so here it is where we see it today. Cool. So we replicated the TESS sector 10 analysis from API. We get about the same answer. So we use the light curve framework as opposed to the pathos technique, and we get about the same value. So that's encouraging. And we apply that same methodology with the light curve framework to sector 37 on the right here in black, and sector 36 in gray. And here's where we got the IGRINS data. So 4 epochs across that time. What are we seeing in the TESS bandpass? So here's the TESS bandpass. So red optical basically, and this object again, it's an ultra-cool dwarf that's super red, and so actually most of the flux is coming out where the TESS bandpass is falling off. So we're actually mostly probing about 8300 to 1 micron is where we're most sensitive in TESS. But a key idea here is the question of, what are you seeing when you see that modulation that we saw back here? So you see conspicuous rotational modulation and sort of more secular variation. Well, what is that? So essentially, we're seeing clouds ebb and flow on the surface, but the question is, what is the prescription for the clouds? Like, what is the spectrum of a cloud? That's a pretty big question, but one key idea is that a sightline to a cloud-free surface is usually brighter than a sightline to clouds, and that's because you're seeing deeper into the hotter parts of the atmosphere. This is very sort of still unknown. There's lots of unknowns here, particularly what condensate species, the cloud thicknesses, what exactly the PT profile is doing, the opacity. So this isn't, there's a lot of work to be done here, but what I recommend if you're curious about these topics is check out this Cloud9 conference coming up in just a bit over a week, where there'll be a whole half day about this. But for now, let's just use a simple, really naive model, because that's sort of all we can do for what the clouds are doing. And here we use just a mixture model, right? A partly cloudy, so some filling factor of clouds times the cloud spectrum plus 1 minus that times the clear or cloud free or cloud holes. And so that's what we're seeing. We're seeing that net spectrum. And I say naive just because these two spectra are computed using this sort of Sonora Bobcat for the clear and a custom clouds for the cloudy. But they're converged separately, so they don't actually share like the same PT profile and stuff. So it's a bit of apples and orange comparison, but it's sort of good enough to get a sense for how these might track these spectra. Okay, so using that and sort of just plugging in different Sonora temperatures, we get a range maybe here. Again, that's very uncertain, but let's pick one of those, and that naive model would say a 10% increase in cloud coverage would result in a mere 1.6% decrease in flux in the test bandpass. In other words, there's not a lot of contrast between the clouds and the cloud holes using this naive model. If you take that to its extreme and assert that one hemisphere, Eastern hemisphere is completely cloudy and one is completely cloud-free, which is ridiculous and pathological, you'd get that you'd never see more than 16% variation in the test bandpass. More realistically, for even more admittedly extreme, but more plausible geometries, you'd get certainly less than 5%. But what you saw in this figure already was that we see 12% variability. And so we can already rule out this naive sort of contrast. So in other words, clouds are much darker than the naive model would prescribe, or equivalently, the cloud holes are brighter. So what we're working on with Caroline Morley, who's a collaborator on this with me at UTexas, is exactly that. So making partly cloudy mixture models where you bake in the clouds into the full radiative transfer and solution to the PT profile and everything. So if you want to ask questions about that, I'm sure Caroline's in the Slack and you can ask me questions about it too. Okay, but for now, we know that the contrast is somewhere in this range. Maybe a 10% increase in cloud coverage would result in a 2 or 5% decrease in the flux or more. We don't really know what this is, but certainly more than what we already saw from the naive sort of mixture model. Okay. Another question you can ask is the surface cloud dominated? So all clouds and little holes, or is it all clear with just little clouds? In other words, what's sort of the predominant surface morphology? And you can't tell that from test data alone. So you could be in any one of these scenarios. Even if you knew the contrast, you don't know, because all you're measuring is sort of the AC component. We don't know the DC component of the light curve. Where is one in the light curve? Where is cloud completely cloud free? So that's where IGRINS comes in. So IGRINS is a high resolution near infrared spectrograph. Currently at Gemini South, it gets you all of H and K in at R of 40,000 in one shot. It's scene limited. It actually uses these custom silicon immersion gratings that I made as part of my PhD. So you could ask me about that too. But the key idea here is that it has really high bandwidth and resolution. So compared to CryRes, which the crossfield work was originally done with, we have just tons more bandwidth. And so that's great. So here's an example of a brown dwarf, just to illustrate that bandwidth, where you get all of H and K compared to, say, Specs Prism mode or something, you get just tons more bandwidth. So the problem is that that's an opportunity and a challenge. So how do you interpret the complex spectra while leveraging all of this new information? There's generally two tools that I prefer. So one is Starfish. I've talked about that at length in other videos. There's one here that you can see. But relevant for this talk is this new one that I made called Golem. So you can pip install Golem. It has documentation and it's on open source on GitHub, permissively licensed, all of that. But the key idea here is that it's essentially, it has among other things, it has an interactive dashboard that plugs into the Sonora models, as well as Phoenix models too. And so this is modeled after the Interact framework that I built within Lightcurve. So if you've used Lightcurve's tpf.interact interface, it's very similar to that in terms of its user interface. But here you can basically just move temperature, surface gravity, log G, rotational broadening, rate of velocity, normalization, all that sort of stuff. So you can just dive into the spectra and get a good feel for it. This is great for students and just great for intuition building. So I encourage you to check that out. Actually, discourage you from using pip. Go ahead and use the developer documentation because this is getting developed so rapidly that we don't get a chance to update pip too regularly. Okay, so just a couple minutes left. Let's dive into the IGRINS spectra. So again, we have 4 visits. And so here's a drill down into the light curve where we're essentially getting different snapshots of the surface state. And again, you see the rotational modulation. We think predominantly of lumen 16B component. And in addition to that, you're getting essentially a secular growth of the surface structures over time. And we're getting snapshots of those. This was through a Gemini South DDT program, so thank you to that great DDT program. And we can finally answer that question I posed earlier, which is, are they mostly cloudy or mostly clear? And the overwhelming answer is that they're mostly cloudy. So on the left is an example with data from lumen 16B, just from one of our 50 spectral orders from IGRINS. And the clear model, so cloud-free, fit very poorly, no matter what you try to do, whereas the cloudy models actually are a pretty good fit. Of course, there's definitely imperfections because the models are imperfect, and we know that, but it's a much better fit. Like I said, that's robust against even no matter how you try to change your temperature. As you scroll up in your filling factor of clouds and try to change log G or something, you really need the high coverage fraction of clouds. So that's one result so far, is that it must be that these surfaces are predominantly cloudy with just like little holes in them. The variability actually isn't very dramatic. And so here's just an overlay where you see, like, at this signal noise of this data, you see some perturbations, but there's also a lot of tellurics throughout, in this example, the K-band, that are comparable in strength. And so to get a real handle on the night-to-night intrinsic variability, we need to do a really careful accounting of the tellurics, and that's still underway. Here's a view of lumen 16A, sort of same story there. And so again, the main idea is that the night-to-night variation intrinsic is relatively small. Okay, I think just one more minute before I take questions. And there's this question of like, well, can you see zonal bands? In practice, it's really hard to see zonal bands because it means you need to see, you need to have a really good underlying model of what your star is doing, what your brown dwarf is doing in the spectrum. So a noise-free template. This was recognized already by Ian Crossfield, and it's common in Doppler imaging. It's even harder in brown dwarfs because you just line blanketed everywhere. There's just nowhere where there's like a line that's isolated. Well, scarcely a place. So I'm tackling that problem with a new framework called Blase, which is an experimental technique to clone pre-computed synthetic models. I have a video on that too, and it uses PyTorch to essentially learn the strengths of the models, and you can train from the models themselves, the lines, and then you can transfer learn essentially those weights or the strengths of those lines to real data. But this is still really experimental. So if you're curious about this, go ahead and ask. All right, here's the takeaways. I'll leave them up because I think I'm already out of time. But if you want, you can ask me questions also about the periodograms, which I have some backup slides for. So I'll stop there and take questions.
All right, thank you, Michael, and great talk. So we started a little bit late, but we'll have time for one quick question. So in the chat, David Ciardi says, how does the IGRINS integration time compare to the rotation period? And is there an effect of smearing in the spectrum as the brown dwarf rotates?
Yeah, exactly. That is a concern, and no. So it's something like 15 net of less than 15 minutes, and so compared to 4 hours. So no, it's not too dramatic. In principle, you might look for within the ABBA nods. Maybe you could try to look for variability on those scales, but no, we didn't attempt to do that.
All right, thanks. Seeing as there are no more questions on Slack, we will proceed to the next speaker, Katharine Hesse from MIT. And she'll be talking about the evolution of the hot Neptunian desert with TESS.
All right, can you see my screen?
Yes. Oh, that's presenter mode.
Oh, hang on just a second.
There we go.
Flipped. Okay, cool. All right. So today I'm talking about how our understanding of the hot Neptune desert has changed with data from TESS. I'm Katharine Hesse, and I'm the TOI vetting and catalog lead at MIT. All right. So the hot Neptune desert, we first became aware of it a while ago. The first hot Neptune that we found was GJ 436b with a period of 2.64 days, and it was detected via RV measurements. I believe it's the red dot that's in that sub-Jupiter desert image on the right. So that was really the first one we found for a while. Around that time in 2011, SASBO and KISS found that even though there were a lot of short period Jupiters with periods below 2.5 days, there weren't any Neptune-sized planets that fit in this range. And this is demonstrated on the right. And then in 2016, there was a paper by Mose et al. That tried to define these Neptune boundaries in a few different parameter spaces. So they found that the radius gap is typically between 3 and 10 Earth radii, and the mass gap is typically between about 0.03 to 0.3 Jupiter masses, or 9.54 to 95.4 Earth masses. And then for the period, typically the upper limit for period is between 2 and 5 days, though some people have suggested it may even go up to 10 days at the most conservative estimate. But this plot at the right just shows the first, I think, 160 confirmed planets. So we have gotten a lot more planets since then from both Kepler and TESS. So now that we know the desert exists, we want to know why it happens. So pretty much what we think is going on is that gaseous planets that are smaller than Jupiter are not massive enough to hold on to their hydrogen and helium atmosphere when they're so close to the star that they experience very strong stellar irradiation. So they'll lose that outer atmosphere. And Lundqvist et al. In 2016 found that the planet gap between 2.2 Earth radii and 3.8 Earth radii, there weren't any planets that had an incident flux higher than 650 times the incident flux of the Earth. So since then, we have actually found a few planets that do fit in that region, and these are what we call ultra-hot Neptunes. So ultra-hot means that the period is less than 1 day. So two examples that we found are LTT 9779b, and this was found in 2020. The period is 0.79 days. The radius is 4.72 days. So a little bit larger than that range that we had before, but not too far outside it. And then the mass is 29 Earth masses. And then we've also found TOI 849 later that year. and the period for that is 0.76, and the planet radius is 3.44, and the mass is 39 Earth masses. So the significance of these ultra hot Neptunes is that they're very good for atmospheric characterization, particularly LTT 9779b has already had 2 atmospheric studies done with data, even though it was just released last year. So one study found that the atmosphere is high metallicity, and another study found that there was evidence of molecular absorption in the atmosphere using Spitzer data. And also just of note, before these 2 ultra hot Neptunes, all of the previous ultra short period planets were more Jupiter size, so with radius over 10 Earth radii, or they were dense, rocky, more Earth-like planets with radius below 2 Earth radii. So taking a look at this definition for the hot Neptune desert, you can see outlined in the yellow dotted lines. Pretty much this paper, Lundqvist et al. Found that the kind of like the lower limit for the Neptune desert for flux, incident flux, was at about 650 times the flux of the incident flux reaching Earth. So that's kind of like that bottom point on the triangle. So I believe they just kind of extended a line upwards. So that's kind of blocking off in a diagonal way. And then the upper boundary, or the lower boundary for radius is 3 Earth radii. So I applied this to TESS data and Kepler data. So this is taking a look at the flux insulation versus the period for all the TOIs and KOIs, excluding false positives. You can see that LTT 9779b and TOI 849 are both marked in the shaded hot Neptune region. And there aren't really too many other planets that made it in there for this one, especially not confirmed. So the open circles are just candidates. And then this is taking a look just at all of the Kepler objects of interest. So excluding all of the false positives, again, you can see there aren't any Kepler confirmed planets within this hot Neptune region, one to define in terms of insulation flux and planet radius. And then looking at the TOIs, we do actually have a few targets in there. So the 2 ultra short period Neptunes that we've mentioned before are in that region. And then I just wanted to take a look. So the 2 ultra short period hot Neptunes are still marked in that region, but just showing how many TESS planet candidates are in that region versus from Kepler, since TESS is pretty good at finding short period planets. So hopefully we'll get some more confirmed with time. And these are our current confirmed planets. So the shaded planets are actually validated. Those don't have masses yet. So the only 2 confirmed hot Neptunes in that insulation flux and radius range are the 2 ultra short period hot Neptunes we mentioned before. So LTT 9779b and TOI 849b. So just kind of the other relation that we looked at is the period radius relation. So this one's less clearly defined than the insulation flux boundary. So you can see not quite all of the points in the plot on the right make it into the bounds, but the data on the right is ground-based and Kepler data. I believe the turquoise targets are confirmed and the other targets are candidates. So basically, two boundaries were made for the hot Neptune region. There's an upper boundary with the equation on the left and the lower boundary with the equation on the right. So I also applied these two TESS and Kepler data. And you can see this is a much larger, actually, back. Oh, I don't know how to go back. But you can see this is a much larger range. So there are a lot more, or yeah, there are some confirmed planets in here, but they're more on the edges. They're not really too much in this emptier region that we see. So these are, again, the Kepler candidates. And these are the TESS candidates. So again, we've got our two ultra short period Neptunes on there for reference, but you can see TESS has a few other hot Neptune candidates as well that are confirmed in the radius period region for hot Neptunes. So again, TESS has a lot more planet candidates in there. So hopefully as those are confirmed, we find some more hot Neptunes in that region. And this is what we have so far. All right. Okay, so this is just kind of an overview of the numbers. So taken with a grain of salt, but this was just going off of periods below 5 days and radii between 2 and 9 days. So what you can pretty much see from this is TESS has found a higher percentage of targets in this radius and period range, and this is because of how TESS looks in many different areas for shorter periods of times, which is ideal for finding short period candidates. So Kepler has a more representative percentage of hot Neptunes, but TESS is kind of biased in a way that is helpful for finding these hot Neptunes. And some of these may end up being false positives as time goes on, but we've already got a few good confirmed ones. So that is exciting. And then just looking forward, we're going to be seeing a new 240-degree area of the northern ecliptic coming up in these next few sectors for TESS that hasn't been seen before due to a rotation. And these candidates are very good for atmospheric follow-up for James Webb coming up. So just a quick plot to kind of show how these candidates are good for atmospheric characterization. LTT 9779b, which we've talked about. This plot is scaled by the transmission spectroscopy metric. So you can see just for scale, LTT 9779b is at a value of 184. And this is TOI 849, our other ultra short period planet. And then this is the emission spectroscopy metric. I think LTT 979b is at 66. So I think I'm out of time, so I'm just going to end on the table of hot Neptunes we have so far, and I'll take any questions.
All right, thank you, Katharine. So in the Slack, we have one question from Jake Clark.
Yeah.
The question is, do we have any other information about the stellar properties of the stellar hosts for ultra-hot Neptunes? Following up, a dye showed that they tend to orbit metal-rich hosts. Have you been able to see the same trends with validated and candidate hosts?
Those are very good questions. There is definitely information on the hosts, but I haven't really looked at it yet. So that is definitely something that would be good to look at coming up.
I guess seeing as there's no more questions, I would like to ask a really quick one. So with the new discoveries from TESS that seem to land right smack dab in the middle of this, the wedge of the hot Neptune desert, do you see the boundaries being redefined?
It's definitely possible. I think they're already somewhat loosely defined. I think as we get more data, we're getting a clearer picture of where these boundaries are with different parameters. So a lot of different papers do have slightly different numbers already. And I definitely think they might be more refined with additional data.
All right, I see a few more questions. I'll choose one real quick. Jane Harrowing says, are you finding an age bias in the hot Neptune's TESS finding?
I have not checked for that, but that would also be a good thing to look for.
Right. So Jose Rodriguez has another question in the Slack. So whenever you have a chance, you can respond to those in the channel. All right. Thank you very much again, Katharine. So next up, we have Jessica Luna from UT Austin. And the title of the talk is Observing Helium Outflows for Irradiated Planets with the Hobby-Eberly Telescope. So whenever you're ready, take it away.
Thanks again. Again, I'm Jessica Luna, a final year PhD candidate at UT Austin, and I'll just jump right into some background of why I think you should care about planets that lose their atmospheres. And really, we can tell from just looking at from a population standpoint that exoplanets that lose their atmospheres really shape the radius distribution of known exoplanets between Earth and Neptune in size. And so this was actually first predicted by theory by Lopez and Portney 2013. And so we're showing on the y-axis radius versus on the left-hand side, the incident flux on the x-axis. And so it's just trying to show the amount of the leftover atmosphere run for a range of planetary parameters. And this was proven to be true later by Kepler from Fulton and Pettigura 2019. And so on the right, I'm showing observations. So the x-axis is actually inverted, but this is the results of Kepler that showed that in fact, there are these two population of small planets that are due to one population losing their atmospheres and one retaining it. And so the big question is really why and how did this one subset of planets retain their atmospheres and why did the other ones lose them? And so we chose to try to answer this question by looking at planets that lose their atmospheres. And so exospheres, helium exospheres were actually first detected using HST from Spakey 2018. And so the top panel on the right is showing the transit depth as a function of wavelength using HST. And with HST, we can observe in the helium bandpass at one data point. And so it's actually not the best telescope or most efficient telescope to use for this method. And so later, Nortman in 2018 showed that you can do this from the ground using the Carmenes spectrograph to confirm a different planet, but that we can use high resolution spectroscopy to resolve the helium 10830 angstrom triplet. On the bottom, it's in nanometers, so it's 1083 nanometers, but that around, by looking and using telescopes from the ground, we can actually measure helium exospheres by measuring the transit while measuring the spectra while the planet transits and while it's out of transit to compare where the essentially the method is that if the transit is deeper, helium line is deeper in transit, then we can infer a helium exosphere relative to the out of transit spectrum. And so we decided to use our large HET access at UT Austin to do a survey of exoplanets using the habitable Zone Planet Finder, HPF, on HET. So it's about an 8 to 10 meter telescope, and really intend to detect any escaping helium atmospheres. And so we've designed the program to observe exoplanets in transit as well as out of transit to detect any helium outflows. Now, HET has a unique design in which its altitude is fixed, and we're constrained to observe each target for 1 to 2 hour chunks, once or twice per night. And so I've plotted on the bottom a TESS folded light curve for one of our targets. And then I've highlighted in just little band passes how much time we can observe using HPF on HET if this was contemporaneous. And so just to show you, our method is to measure an out of transit spectrum the night before, during transit, if possible, the same night out of transit, and then the following night as well, to obtain an adequate, really baseline to make sure we understand what we're really observing due to HET's unique design constraint. And so we decided to start with something we know. And so I previously mentioned that Nortman 2018 actually detected WASP-69b's helium exospheres from the ground using Carmenes. And so this is our proof of concept that HPF can actually achieve the same. And so this is a plot of spectra using HPF on HET for WASP-69b. In black, we have the transit. In the colors, we have compares the spectra for out of transit nights. And so really the takeaway is that we find consistent results with Nortman 2018, in which we find an excess in the helium depth during transit compared to our out of transit nights. And so our sample to date contains a wide range of planets, with surface gravities covering a large parameter space and host spectral types ranging from F to M stars. And so I'm plotting here stellar effective temperature versus planetary surface gravity. The gray dots are all possible transiting planets we can observe with HET and HPF. The dark blue circles are targets we've observed at least one transit for. And the light blue squares are targets where we haven't observed a transit, but we have observed rigorous essentially monitoring of the star so that we can get a better handle of how the star's variability affects different spectral features, not only helium, but lines like calcium H and K and other activity indicators that we're exploring. I've also highlighted in red previous detections for known helium exospheres. And so we can actually slice, if I slice this sample to show instead of planetary surface gravity, planetary radius, to really highlight that we've mostly to date observed hot giant planets, because that's really, there were only, due to how many bright stars we had to observe, we were just limited by what was available. But TESS has increased the number of smaller planets around bright stars, which are the exact targets that are perfect for this type of science. And for these targets, we can get very high fidelity measurements of helium exospheres. And so I've highlighted in black stars two new confirmed TESS planets that we've observed with HPF and HET. And so we want to gently ask anyone willing to, that we need more validation and follow-up confirmation of TESS planets in the Northern Hemisphere between declinations of 10 and 70 degrees. And this is largely based on HET's constraints in declinations that we can view. There are 3 times more confirmed TESS planets in the south than in the Northern Hemisphere, which is great. We just need more confirmed in the north that we can follow up and search for helium exospheres. So to quantify a little better how much TESS has helped, I've plotted some histograms of the number of planets we were able to observe prior to TESS compared to now. And so the left-hand side is showing the J magnitude, the brightness used for HEPF observations. On the right, we have the planetary radius. And so really just highlighting that we have many more planets that are bright and also small. And because we had so many gas giant planets, we really wanted to go after smaller planets. And so just again, reminding everybody, there's 3 times more, or really three times less confirmed TESS planets in the north than there in the south. So anyone willing, please confirm more of those planets. So next, to show some preliminary analysis, please do not tweet this. We're still looking into this data. But this object, for which I'm not telling you the name, shows repeatedly a stronger helium line during transit than compared to out of transit observations. And so on the top panel, I'm showing the normalized flux for different observations. And in black again is the transit. In the bottom, I'm showing the in transit divided by each out of transit observation. Additionally, I've highlighted the wavelength ranges for different features. Highlighted in yellow is the silicon line, which is largely unchanged compared to other lines, which should stay it should stay the same, versus the helium line in the middle, highlighted in that purple shade, is clearly deeper by about 5% than the out of transit observations. And so this is repeated across two transits that we've seen. And just a warning for anybody trying to do the science, sky emission lines are very precarious. You really need to watch out that the time of the year you're observing these stars does not blend with the helium line, as I'll show in a second. And so really this is just trying to show that the helium line does not correlate with the sky emission lines or even the silicon line on the left-hand side. Something very interesting we found was that for another planet, a different planet, we repeatedly see deeper helium absorption on the day of transit and the night prior. And so this is actually across 3 transits, one of which on the right-hand side, this transit was just serendipitously contemporaneous with TESS. So it's great for us in terms of really pinpointing why we're seeing deeper helium absorption the day before as well as during transit. Could it be star-planet magnetic interactions? We're still looking into this, so stay tuned to figure out why this data is so peculiar. So the two of the hottest stars in our sample are showing deeper helium absorption. And so this is just a reminder of that stellar effective temperature versus planetary surface gravity. 2 of the hottest stars in the sample are the ones that show deeper helium absorption during transit. Now, theoretical models have shown that K-dwarfs, which are highlighted in the graph where the 2 red lines are, and so that's just encompassing where K-dwarfs sit on this graph, that they actually produce enough short EUV flux to produce the helium in its metastable state to produce the 10830 angstrom helium line. And so we're not actually seeing that trend. We're seeing that the data that looks most interesting is around the hottest stars. And so stay tuned to find out what that means. So we have planned in the next trimester for HPF and HET observations contemporaneous with TESS for young planets to explore next how age affects atmospheric mass loss. And so this is, most of our sample is for field age stars. And so I'm showing the planets we have proposed to observe and their ages versus their stellar effective temperatures. And so stay tuned for these results as we're going to be observing these very soon. So I'll just briefly summarize that we have a very large survey using HPF at HET to detect helium exospheres for a wide range of planets covering a range of surface gravities, host stellar spectral type, planet radii, and age. And then just a reminder that we're really needing and limited to the amount of TESS follow-up planets that are in the Northern Hemisphere. And so really follow-up confirmation of TESS candidates are enabling high quality observations to measure escaping helium atmospheres via the 10-830 nanometer helium feature. And this is really to explore what drives atmospheric mass loss. And I just want to thank you and highlight that this is done with a large team of people, not just me, Caroline Morley, the PI, my advisor, as well as more junior members like myself, and graduate student Quang Tran. Michael Gully-Santiago has done a lot of the legwork too of the analysis, as well as some undergrads, Aishwarya Ganesh and Joel Burke, who I believe both are, you can both look out for in your grad student applications. So thank you, and I'll take any questions.
Thank you, Jessica, for the wonderful talk. So in the Slack channel, we have one question from Dave Latham. Responding to your plea for more validated targets in the north, how bright do the host stars need to be? And do you have any upper limits on the planet radius and or effective temperature of the host star?
Yeah, so our faintness limit for the north that we're using is J of 11. Anything fainter than that, and we start to struggle on the amount of signal we can obtain for our exposures. And so we're really just limited to a J of anything brighter than JMAG of 11.
All right, and to finish with one quick question, Brian Jackson says, do you have any constraints on mass loss rates? We don't, as of yet. We will very soon. We're working really hard to get some of that out, taking some of the preliminary analysis and converting that to mass loss rates is really the next step. So stay tuned to hopefully see that paper up. All right, thank you. So
Thanks.
The last speaker of the session is Vardan Adibekyan from the Institute of Astrophysics and Space Sciences, and he'll be talking about the chemical link between stars and their rocky planets. So take it away.
Thank you, Jan. Thank you for the introduction. Do you see the proper screen?
This is presenter view here.
Okay. Is it better now?
Yes.
Okay, and you can see also the cursor?
Yes.
Okay, perfect. So thanks again for the introduction, and thanks for the organizers for giving this opportunity to me to present our latest results that we submitted to Science. We already had 2 rounds, very constructive rounds with the referees, and the last version we submitted some time ago, and hope to have the results accepted, the paper accepted by the editors soon. So this work was done in collaboration with the people that you can see in your screen. And it's about the chemical link between stars and rocky planets. So we know that the young stars, at the early stages, they are surrounded by the protoplanetary disks, and some material of these protoplanetary disks condense into planet building blocks, and the rest eventually accretes into the stars. In other words, we know that the stars and planets both grow from the accretion of the same material. Because of this common origin, it has been usually assumed that there should be the composition of planet building blocks, and even the composition of rocky planets should be similar to the composition of the planet or stars, at least for refractory elements. And in fact, if we look at the solar system objects, we see that there is a very good match in the composition of stellar photospheric abundances and the meteoritic abundances, at least for the refractory elements. Here you can see on the left figure. And also, if we look at the rocky objects, rocky planets in our solar system, we know there is a good similarities between the magnesium over silicon ratio and iron over silicon ratios in rocky planets and in the sun. The exception is Mercury, but we know that most probably this planet had a peculiar origin or evolution, and some like giant impact will be responsible for this extra enhancement in iron of this planet. So the literature is rich in very interesting works trying to link the chemical composition of stars and the rocky planets. Here I highlight two recent works by Plotnikov and Valencia, and also the other one by Schulze 2021. And I suggest us all to follow the exoplanet panel discussion today. We will learn more about it, and also you can watch the recorded talks by the panelists, especially the one of Diana Valencia is very similar. The subject is very similar to what I'm presenting now. And on the left figure, I highlight our work in 2015, where we tried to see the composition of three stars hosting planets that were lying on the Earth-like composition curve on the mass radius diagram. So we wanted to see whether, since these planets have the same composition because they lie on the same compositional curve, we wanted to test whether their host stars also have the same composition and whether their composition is similar to the Sun. But the sample consists of only 3 planets. So our current sample includes 21 low mass planets that with precise RV measurements. So the masses come from the radial velocity measurements, and the precision is better than 30% relative precision. And the radius are small, because they lie below the radius valley, and again the relative precision is better than 30%. So we have 21 planets, and during the reviewing process we added this TOI 561b. This was a recent discovery. It's announced as unusually low density super Earth that is orbiting a metal poor and old galactic tick star belonging to the galactic tick population. So for all these planets, I have to stress that these planets are hosting around sun-like stars. We gathered spectra from different telescopes and instruments. The list of these telescopes or instruments you can see on this bottom part of the slide. So we used high resolution spectra to determine their magnesium, silicon, and iron composition in a homogeneous way, and their distribution on magnesium over iron, silicon over iron, magnesium over silicon, and versus metallicity you can see on this plot. And based on these abundances and using a very simple stoichiometric relations from Santos 2015 and 2017, we determined the iron mass fraction. This is basically the iron mass fraction relative to the total mass, which is iron and silicates in this case. Yeah, please note that the iron mass fraction is not equal to the iron composition of the stars. Stars that have similar iron abundances but different magnesium and silicon composition can have different iron mass fraction. This difference in abundance ratios is due to the galactic chemical evolution. Stars formed at different places and at different times in the galaxy will have different compositions. So having this about iron mass fraction of the stars, that we assume that they are proxy of the iron mass fraction of the planet building blocks, we look for the correlation between the density of these planets, these potentially rocky planets, and this iron mass fraction. We had to normalize these densities to the density of a planet with Earth-like composition for a given mass. This normalization is very important because the stars with the same composition but having different masses will have different densities because of the mass contraction. So we found a very good statistic. We found a statistically significant correlation between these two parameters. And you can see that this low density of the TOI 561b, in fact, matched well the general trend that we observed. On this plot, you can see also the positions of the solar system rocky planets, the densities, and this line corresponds to the iron mass fraction of the Sun calculated with our model. So here you can see also that the group of 5 planets that are potentially super Mercuries, they have higher densities than the rest of the planets, and with appreciating the possibility that these super Mercuries may have a different origin, we tested whether the correlation between the densities of planets and iron mass fraction of the stars holds also for super Earths, for this group of planets, and it is. You can see also that there is a relatively large dispersion around this regression line, and we wanted to see whether this, and also the points of these points have relatively large errors. We wanted to check whether this dispersion could be due to the let's say the equilibrium temperature of the planets. They have a range of temperatures, but we didn't find any trend. So the next step for us was to determine also iron mass fraction of the planets. So using the model of Caroline Dorn, and assuming that these planets are made of rocks, they have a metallic core and also silicate mantle, we estimated the iron mass fraction of these planets. We ignore the volatile layers for these planets. And on this figure, you can see the comparison of our estimated iron mass fraction with the literature results that have more direct measurements. And overall, there is a good agreement. So in this figure, we show the iron mass fraction of the planets using I have to say that for these interior models, we used only the mass and radius. So basically, these estimations are based on the density of the planets. So on this plot, I show the iron mass fraction of the planets versus the iron mass fraction of the planet building blocks. It's estimated from the host star composition. And again, there is a statistically robust correlation between the two variables. And this correlation is true whether we include the super Mercuries or we exclude them. So there is a correlation, and from this figure you can also see that majority of the planets have iron mass fraction that is larger than the iron mass fraction of their host stars. That's another important result that we found in the paper. And also you can see that most of these potential super Mercuries are orbiting stars that have high iron content or high iron mass fraction. So to conclude this part, or to summarize, we see that there is a correlation between the iron mass fraction of the planets and their host stars, and that the correlation is not one-to-one. I suggest you also to look at Plotnikov and Valencia, like they looked at the core mass fraction of the statistical center of the planets and their host stars. They found also a similar results. And perhaps this non-one-to-one correlation needs to be replaced the typically used one-to-one correlation when trying to characterize the interiors of the planets with some constraint from the host star composition. And this fact of non-one-to-one correlation is most probably related to the planet formation processes in the disk. If we follow the work of Agushin and collaborators 2020, this author suggested that in the protoplanetary disk, if the planets are formed next to these called rock lines, these rock lines are similar to the ice lines, but for each element you have a rock line, a rock line like iron line, magnesium silicon line. This depends on the temperature in the disk. So basically, if the planets are formed close to these rock lines, they can be enhanced in a given element. In this case, if the planets are formed close to the iron rock lines, then they will be enhanced in iron when compared to the average disk compositions. Yeah, and during the talk, a few times I mentioned about the possibility of the presence of super Mercuries. In fact, if you look at the densities of these planets, you can see that there seems to be a separation between the densities of super Earths and super Mercuries. The error bars are still large, but if this hint is confirmed, this could perhaps mean that the giant impact, at least alone, cannot be responsible for the higher densities or higher iron mass fraction in these super Mercuries, because of its nature. It's a stochastic process, and one would expect to have a continuous enhancement of iron or density in these planets, while we see, perhaps we see a gap between the two. On the right panel, I show the iron over magnesium plus silicon estimated for the planets using the interior models that we used, versus the composition the same abundance ratio, but for the host star photosphere. Again, we see the large separation between the two groups. And we can see that there is a clear correlation between these two variables for the super Earths. And it's difficult to say anything for the super Mercuries. I mean, there are only 5 comets. But this is perhaps will be interesting to look at it in the future when we have more data, and obviously when we have more data from TESS. So this is my conclusion, that rocky planet composition depends on the chemical composition of the protoplanetic disk and contains signatures about planet formation processes. Thank you for your attention.
Thank you, Vardan. We have a couple of questions from the Slack channel. First up, from Brian Jackson, we have, he asks, the range of F-star for your stars only spans a few percent and goes up to 10% if you include TOI 561. Is your stellar sample skewed to large values in terms of its metallicity? And do you have any sense for how that might bias your results?
Again, we selected only FGK dwarf stars for which we are able to get the good abundances. And I have to say that we didn't find strong correlation between the metallicity and density or iron mass fraction in the planet. This is a correlation between iron mass fraction, which is iron over silicon over magnesium, or iron over over silicon and magnesium. So the correlation is much, it's not just the effect of metallicity. So I don't expect any bias, and I have to say that the I don't remember exactly the numbers that you said, that I don't think that sample has many F stars, because these are low mass planets, and the detection of these low mass planets around F stars should be a bit more difficult, I would say. I have the range, but the range should be from 4,500 Kelvin to 6,300, I think, Kelvin. Yeah, there should be a few Fs.
All right, Andrew Vandenberg has a question. Does the correlation change if you use the mass of TOI 561b from Wise et al., which is higher density?
TOI 561, right?
Yes.
Yes. So in the initial submission, we didn't have this planet. We discovered about this planet in the meanwhile we edited. The slope changes slightly. I mean, it changes a bit because it's a kind of an extreme point, but the statistical significance remains the same. I mean, it adds a bit more significance, but not much. I have to say that we are a bit conservative about the exact slope of this correlation, because the data has relatively large errors. What we are sure is about the correlation, but perhaps in the future, when we add a bit more planets, we will be able to better characterize exactly the relation.
All right, thank you. And I'd like to take this opportunity to thank all the speakers of this session for a great series of talks. And for everybody who's participating, the next exoplanet session will be after the midday break, starting at UT 1930. That's 3:30 p.m. Eastern. And it'll initiate with a panel discussion and then proceed with invited and contributed talks. So I would like to thank everyone for tuning in, and see you next time.